Hi, everyone. My name is Philippe. I'll be one of your speakers this afternoon. I work with the solutions architecture team at Astronomer. And previously, I worked in data analysis and data engineering in the financial sector with both large and small institutions. I'm a big Python fan and a big Airflow nerd. So welcome to my talk. This is part 3 of what I'm hoping to become a series of technical deep dives on various Airflow subsystems. Last year, we talked about cluster policies, and in 2022, we talked about the Airflow logging subsystem. And this year, we're going to talk about scheduler internals, but most specifically looking at the path that the task takes from instantiation to actually running. So this year, we're going to be, like I said, talking about the Airflow scheduling process, and yeah, specifically the code path that the task takes from instantiation to execution. So we're going to cover the following: Airflow task scheduling and execution components and the role, the scheduler initialization process, the task scheduling framework at a high level, the scheduler timers and what they do. We're going to look at how DAG runs are created. Afterwards, we're going to look at what's called the scheduler critical section and how it handles task instance creation. We're going to look at how executors pick up task instances, specifically looking at Celery exec and queue exec. And we'll look at how a task actually runs, also on Celery exec and queue exec. So we'll begin with a short reminder of the main Airflow components. So the scheduler is responsible for adding jobs to the queue when their dependencies are met and triggering the execution of tasks. The DAG processor parses, processes, and serializes the DAG files. It can either run as part of the scheduler or standalone. The executor actually runs or submits a task for execution. It runs as part of the scheduler. And in this talk, we're only going to focus on queue exec and Celery exec, but other implementations exist. The worker actually executes the task's payload. It runs an operator's execute method. And this can either be a long-lived process, as in the case of Celery exec, or it can be ephemeral, such as with queue exec. Before we go further, I also just wanted to offer a quick reminder, or primer rather, of some important Airflow concepts. So this is a diagram that I originally made for my talk last year, but it's still relevant today. So in a nutshell, a DAG is a DAG. A task is the implementation of an operator that belongs to a DAG. A DAG run is the instantiation of a DAG at runtime. And a task instance is the instantiation of a task at runtime, which belongs to a DAG run. In my view, there's two main phases, for lack of a better term, in Airflow. So the first phase I usually refer to as the DAG definition phase, and the second phase as DAG instantiation phase. And while DAG definition is mostly within the DAG processor's realm, DAG instantiation is the scheduler's responsibility, and that's what we're going to talk about today. So yeah, the scheduler's main job is to instantiate the concepts defined in the first DAG definition phase, and then turn them into units of work and schedule them for execution. This is how it fits in the overall task execution framework or architecture, with the first two boxes here roughly corresponding to the operations described on the previous slide. In short, when a DAG is up for execution, the scheduler creates a DAG run and associated task instances. When task instance dependencies are met, the scheduler sends them to the executor, which is responsible for ensuring that they run. The rest of the talk is mainly going to focus on the process illustrated in the yellow and blue arrows here, with the yellow arrows showing operations primarily related to scheduling tasks, and the blue arrows showing operations primarily related to executing tasks. And note also that on the execution front, we're only going to be covering queue exec and Celery exec, as we said, but yeah, other implementations do exist. So yeah, this is the scheduler initialization process at a high level. The first step is to actually start the scheduler, which is generally done by invoking the Airflow scheduler command from the command line. This is going to load a bunch of settings and eventually invoke the run scheduler job method. Run scheduler job will instantiate a scheduler job runner, which is the component responsible for actually running the scheduler job. The actual running of the job is performed by the run job function, which is imported from the job module. A job in Airflow is a background task with a status that is tracked and reported. There's a few types of common jobs in Airflow, such as the scheduler job here, but there's also worker jobs, trigger jobs, task jobs, et cetera, et cetera. In this presentation, we're mostly going to be focusing on scheduler job and worker jobs. So yeah, at the point where we're at here, the scheduler is actually starting, and this does 2 or 3 things, depending. First off, we start the executors. Executors with an S because we now have first-class multi-executor support in Airflow since version 2.10, which was just recently released. If we're running our DAG processor in the scheduler, that is not using a standalone DAG processor, we initialize the DAG file processor agent, but we're not going to cover this process here in this talk. Finally, we run the actual main scheduling loop with the run scheduler loop method, which is part of the scheduler job runner class. And at this point, we're ready to talk about the main scheduler loop. And this is where pretty much everything happens. So there's multiple steps here. The first one being the initialization of the loop timers, which define operations to be ran on a set interval to perform maintenance operations on the objects the scheduler works with. We'll talk about them in more details shortly. We then enter the actual scheduler loop, which is separated into 3 main parts. So first off, the DAG run and task instance scheduling logic, which are contained in the do scheduling method. Then afterwards, for each executor, we perform a heartbeat. The executor heartbeat is an important step as it's the code path that implements a step of sorts in the executor logic. Finally, if necessary, we perform a scheduler heartbeat. By if necessary, we mean that we only perform a heartbeat if a span of time defined by the scheduler heartbeat sec configuration parameter has elapsed. The timers are an instance of the event scheduler class, which is a class that inherits from the sched standard library module, but it implements an infinite loop. So they perform important maintenance functions, such as task adoption, which is the process by which a scheduler adopts a task that appears to be unmonitored, checking trigger timeouts, detecting zombie tasks, which are tasks that are considered to be running but that haven't produced a heartbeat in a while, so they're probably dead. Failing tasks that are stuck in queue, which can happen, for instance, when a user tries to run a task against a non-existing queue, or if no pull slots are available for a very long time. Cleaning up the datasets table, and removing stale DAGs, which are DAGs that exist in the serialized DAG table, but for which we cannot find a Python source file. Since these methods are only called to fix non-fatal exceptions and resolve inconsistent situations, they're not called on every iterations of the scheduler loop because that would be too resource intensive. So moving on to the do scheduling method here, the first step in the do scheduling method is to create DAG runs for DAGs that need DAG runs created. We do this by looking up the next DAG run create after column in the DAG model table. This is limited by a parameter called max DAG runs to create per loop because this is a relatively expensive operation. We also order this query by next DAG run create after in order to select the DAGs that are scheduled to run the soonest, which makes sense. After the requisite number of DAG runs has been created, we move on to the next step, which is attempting to start DAG runs which are in queue. In this operation, we check to ensure that we aren't creating too many tasks, which could cause the max active tasks parameter per DAG to be exceeded. There is a limit applied to the query run by this operation because it requires a row lock, and attempting to lock too many rows could cause other schedulers to be starved. And that would defeat the purpose of having an HA scheduler, for instance. That limit is controlled by the max DAG runs per loop to schedule parameter. After that, we fetch DAG runs that are in the running state and attempt to schedule their task instances. This operation also acquires a row lock, and the same parameters and caveat applies. Finally, we enter the critical section, which is the section where the scheduler examines task instances and attempts to queue them, effectively sending them to the executor for execution. So when we enter the critical section, which is arguably the most important part of the scheduling process, as it's where task instances are getting queued for execution by the executors. The first part of the critical section is a lookup to figure out how many task instances we should examine exactly. This is done by taking the minimum of either the max TIs per query parameter or the parallelism value in the Airflow configuration if max TIs per query is set to 0, which essentially means infinity, or parallelism in this case. Then we enter the queuing process itself. So first we require a lock on the rows of the pool table in order to get a sort of global lock on scheduling. What this means essentially is that only one scheduler can schedule task instances at a time, but the other schedulers can perform other tasks, such as creating DAG runs. Once the lock is acquired, we select up to max TI's task instances based on the various limits defined in the Airflow instance and current state, and queue them for execution. There's two pitfalls of note here. First off, the optimal max TI's value has a large impact on scheduler performance, and it's really, really hard to tune properly. There's a trade-off because large values will cause each iterations of the scheduling loop to take longer, but they'll also perform more work comparatively. Second off, while task instances are selected amongst the running DAG runs, they are ordered by priority weight, which is a global value that spans all DAG runs currently executing on the Airflow cluster. This can be a bit counterintuitive because in effect it means that task instance scheduling priority is sort of like decoupled from DAG run scheduling priority. And furthermore, confusion can be a bit compounded because priority weight is calculated according to a weight rule. So the default weight rule downstream sums the priority weight of all descendants of a task in order to calculate the priority of a task's value. What this means is that the structure of a DAG can have a large and unintended consequences on scheduling priority. It's hard to describe all scenarios that can happen, but consider in Airflow instances where there are very deep DAG coexist with very shallow DAGs, as pictured above. If DAG A is scheduled very aggressively, it's possible that task instances in DAG B will never be examined, depending on the max TIs per query parameter. This issue can make DAGs appear starved, which can be a frustrating experience for a user, in a multi-tenant environment especially. Anyway, moving on. At this point, locks are released and other schedulers are able to schedule task instances from here on. We're out of the critical section, and we reach the executor heartbeat process. The executor heartbeat is the process used to trigger new tasks and queue them for execution. We start by calculating open executor slots, which is done by subtracting the number of currently running tasks with the value of the parallelism configuration. The parallelism config is defined as the number of tasks that can run concurrently on an Airflow cluster per scheduler. After this, we call the trigger tasks method, which will examine up to the number of open slots computed previously. If we have executor and pool slots available, we call the process tasks method. In some cases, process task will submit tasks for synchronous execution by the executor. And that's actually the default case. However, some executors, such as Celery, notably, do not work with standard asynchronous execution at this point, and they override process tasks with their custom logic. We'll talk about this a bit later. Finally, we call the executor sync method, which is executor specific. The sync method is nominally responsible for reconciling task status. So we're going to talk about the Celery executor execution process, but first we need to take a look at how it's initialized. Celery executor initialization is a relatively simple process. In general, executor initialization is a two-step process where the init method of the executor is called when it's initialized, and the scheduler calls a start method on the executor when it starts. However, the start method of the Celery executor doesn't do anything, and everything is prepared in the init method. So there's two important objects here that are initialized to take into consideration. The first one is the bulk state fetcher, which is a class that implements logic to fetch tasks results from Celery as efficiently as possible, but depending on the result backend that's in use by your Airflow instance. For instance, if you're using like a key value backend or a SQL-based backend or something else, the most efficient way to fetch result in bulk differs. And the second one is the task map, which keeps track of tasks that the executor is currently managing. With Celery executor, the execution path starts in the process tasks method, which is overloaded from base executor. This method will gather tasks and then call the send task to Celery method. Since sending tasks to Celery cannot be performed in bulk, we use a process pool to parallelize this part of the process. The executor will create a process pool executor with a number of processes equal to the sync parallelism configuration parameter to dispatch tasks to the Celery backend. That's done in the send tasks to executor method, which in turn calls the apply async method from the Celery library to perform the actual dispatch. The return value of the apply async method is a feature that will allow us to check on the Celery task results in the future. So we store it in the task collection for future use. At this point, the task should be queued in the Celery backend and available for workers to pick up. So more on that a bit later, but let's first talk about the sync method, which runs right after. The sync method is responsible for reconciling task states. It calls update all task state, which fetches task status from Celery using the bulk state fetcher, and updates task instances states based on the Celery task state. Tasks need to run before their task can change, though, and in Celery, this is done by a Celery worker. The apply async method seen a bit earlier actually creates an entry in the Celery broker backend, providing a reference to the task instance that's queued for execution, as well as the actual Airflow command to run to execute the task. This is done by actually creating a sub-process that runs Airflow task run command with the appropriate parameters. And this is where your task payable finally actually executes. Once execution is complete, the results are passed to the result backend, and this is what Celery Executor obtains from the bulk state fetcher during the sync method to reconcile task instance states. So yeah, in a way you could say like the Celery worker is actually not really Airflow code per se, but it's the worker itself, not the executor. It's generic Celery worker appropriately configured for our purposes. With that being said, there's two configuration parameters that are important for scalability here. The first one is worker concurrency, which is the number of tasks that can run concurrently on a single worker. Depending on your environment and your workloads, it may be more beneficial to run like a few larger workloads, workers running a large number of tasks, or maybe many smaller workers running a small number of tasks, or many large workers running a relatively smaller number of tasks as well. It really depends on your workflow patterns. For instance, executing queries on a Postgres database is completely different than running heavy Python workloads directly on workers. The second parameter is worker prefetch multiplier, which defines the number of tasks that a worker should prefetch from the broker backend. And by default, that's set to 1 because it's possible to starve workers by setting this value too aggressively. However, it can be beneficial to increase it if your workload patterns are composed of like a large number of very short-lived tasks. So at the high level, that covered Celery. So let's talk about kubeexec a little bit. The kubeexecutor initialization process is a lot more complex than Celery's, and that's because it tracks a lot more state than the Celery executor. The main components that we instantiate are a task queue, which is responsible for holding tasks queued for execution. The results queue, which holds results from terminated tasks before they can be processed. An Airflow Kubernetes scheduler, which is responsible for scheduling pods on Kubernetes. That's an internal component to the Kubernetes executor. And a kube client, and an event scheduler to perform maintenance operation on schedule. Since some of these components are relatively complex to instantiate, we make use of the start method for the actual instantiation. It looks a bit like this. So the executor is initialized lazily on access by the jobs.executor's property. Then the heavy components, the kube client, the Airflow Kubernetes scheduler, and the event scheduler are initialized in the start method, which is called by the scheduler job runners under execute method. If we recall, this is one of the first methods called during the scheduler job runner initialization process. The Airflow Kubernetes scheduler initialization process is also relatively complex. First off, it takes the Kubernetes executor's result queue and kube client as arguments. And second off, it creates Kubernetes job watchers. Kubernetes job watchers or kube watchers are components responsible for listening to events in the kube namespace in which Airflow launches tasks and relaying them to the executor. And they run a separate process. Unlike with Celery, in kubeexec, the executor does not submit tasks for execution synchronously in the process tasks method. Rather, process tasks calls the execute async method in the Kubernetes executor instance, which generates the configs required to create a pod spec and a command to run the actual task payload. These values are inserted as tuples in the kubeexec task queue, which is examined in the sync method. The sync method in kubeexec is very complex. It's called, once again, during the executor's heartbeat method. As a first step, it's going to call the Airflow Kubernetes scheduler sync method, which is responsible for reconciling pod status. The sync method of the Kubernetes executor deals more with task instance status reconciliation, while the Airflow Kubernetes scheduler sync method deals more with reconciliating pod states. So the Airflow Kubernetes scheduler's sync method will get all items from the watcher queue. The watcher queue is a queue that is filled by the kube watchers. When the kube watchers start, they begin to continuously monitor the Kubernetes namespace for which they're configured and process events related to Airflow task pods. When a relevant event is found, it's put in the watcher queue, which the Airflow Kubernetes scheduler reads from. If the Airflow Kubernetes scheduler finds a task that is done, it gets put in the result queue. Then the Kubernetes executor goes through the result queue and changes the state of the task instances accordingly. Then we can move on to the second step of the process, which is creating pods for new tasks. We start by reading from the task queue populated by the execute async method. So we grab up to worker pods creation batch size pods, which is an Airflow configuration parameter, worker pods creation batch size, which essentially defines how many pods we're going to be able to create per scheduler iteration. This parameter is in place because creating pods is a relatively expensive operation, as it requires making API calls to the Kubernetes API server. And we don't want to block this scheduler loop too long. As always, though, the proper value depends on your requirements. So we loop through the tasks acquired from the queue and call the Airflow Kubernetes scheduler run next method on them. The run next method will construct a pod for the task using logic from the pod generator class and pass them to the run pod async method. Finally, the pod will be submitted to the Kubernetes API and it will start. So this pretty much covers at a high level the process of scheduling a task from initialization to execution in Airflow. As takeaways, well, the scheduling process follows the same steps almost at every iteration. We create DAG runs, we queue DAG runs, we queue task instances, we create new task instances, and then we run the executor. A task always travels or moves from the scheduler to the executor to the workers. And finally, configuration parameters are numerous and need to be tuned carefully according to your workload patterns. Thank you.